Hi, I'm Akshima Negi, a graduate student at Department of Physics. I'm going to present the work being done by the Ice Cube team at UTA on searching for decoherence from quantum gravity at the Ice Cube South Pole Neutrino Observatory. So, quantum nature of gravity still remains a fundamental open question that is not explained by the standard model. There are various efforts being made to test theory of quantum gravities, but these are very hard to observe as the effect of quantum gravity only becomes apparent at extremely high energy scales, which are currently not accessible by our current particle accelerators. So, in this work, we look for decoherence, which is a direct consequence of quantum gravity via neutrino oscillations. In standard model, neutrinos comes in three flavors, and a neutrino which is created in a specific flavor can change its flavor as it travels through space. This is a very well established phenomenon known as neutrino oscillations. The oscillation pattern depends on the energy of the neutrinos and the distance that it travels. And for large distance scales, it becomes a very sensitive probe for various searches of beyond standard model physics. So, if gravity has a quantum nature, the principle of quantum mechanics dictates that as we go to extremely small scales, there should be fluctuations in space time curvature. And in extreme cases, these fluctuations can create virtual black holes. And when neutrinos interacts with these virtual black holes, it will modify the oscillation pattern, leading to dampening of the oscillations, otherwise known as oscillation decoherence. We study these oscillations at Ice Cube Neutrino Observatory, which is a very large scale neutrino detector at Ice Cube at South Pole. The Earth is constantly being bombarded by extremely high energetic particles, which, when they interact with our Earth's atmosphere, decays into neutrinos. And these neutrinos will change their flavors while the oscillation as they are traveling to Earth until they are detected at Ice Cube. And then at Ice Cube, the energy and direction of these neutrinos are reconstructed to get a neutrino energy spectrum. Now, to search for decoherence, we look for deviation between the muon energy spectrum that is expected from the standard model and the one that is being observed at Ice Cube. So, in presence of decoherence, we see that there should be a decrease in atmospheric neutrino flux at high energies than the one that is predicted from standard model. And in this analysis, we basically use to describe the strength of decoherence, we use the parameter gamma naught, and we will take into consideration various energy scaling because to which like the effect of energy on decoherence. We take the models with energy scaling of n is equals to 0, 1, 2, and 3 for this analysis. And the dashed line here shows what is the expected result if it's consistent with the standard model. That is, if there is no decoherence, the dashed line is what we would expect as our result, and the shaded region shows what is the allowed region, and taking into consideration all the uncertainties, and the solid line shows the result that we get from the data. And as we can see that the data is consistent with the standard model within all the uncertainties. So we have not observed a decoherence signal, but this with using these results we can put constraint on the decoherence parameter as all the values which are to the right of the data are excluded. So we have put constraint on the decoherence parameter, and in this plot we have compared our constraint with the constraint that has been put by other neutrino experiments. As you can see that we have gotten the strongest constraint on the decoherence parameter by several order of magnitudes. And when we check the seat for n is equals to 2 model, we have constraints stronger by up to 6 order of magnitude, which is 10 to the power 6 times stronger than the current constraint. So the Ice Cube team at UT has set the strongest constraint on neutrino interaction with quantum gravity